Yesterday, our previous class is convergency of infinite series of positive terms. Here in this one, we have studied one example, introduction of one example. A series is giving three types of answers by choosing the methods here. First answer is 0, second answer is 1 by 2, and the third answer is 1. Okay, three different types of answers is given. Now, okay, a series is giving three types of answers. Okay, today I want to start a 53 page convergency of an infinite series. I will open this one. Okay, here open this page every time. Okay, this is the our today's lesson convergency 4.2 convergency of an infinite series. First of all, definition. First, given a sequence un, here un is a sequence of real numbers. The sequence Sn defined by Sn is equal to how much here? K is equal to 1 to summation K is equal to 1 to n. Uk is equal to u1 plus u2 plus n so on. Un is called a sequence of partial sums of the infinite series. Okay, here summation n is equal to 1 to infinity is denoted by un. Here, if Sn is converges to S as n tends to infinity, the series is said to converge to the sum S and is called the convergent series. Okay, therefore it is denoted by summation n is equal to 1 to infinity, un is equal to how much it is? Yes, otherwise the sequence Sn diverges, summation n is equal to 1 to infinity, un is divergent. First of all, here we are taking partial sums. We are taking here partial sum, nth partial sum. Okay, here you can take here it is the left hand side is a sequence and right hand side is a partial sums. Okay, how to write this one? First of all, to take here S1 is equal to suppose U1. Okay, next one S2 is equal to how much? U1 plus U2. And next one S3 is equal to how much it is? U1 plus U2 plus U3. And next and so on. And so on here. Sn is equal to how much here? U1 plus U2 plus U3 plus and so on plus Un plus Un. Okay. This is the type of here series. Here S1 is equal to 1 is the first term. Here first term. Next S2 is equal to U1 plus U2 2 terms. Here. S3 is equal to U1 plus U2 plus U3 is equal to 3 terms. Next one Sn is equal to U1 plus U2 plus U3 plus n so on. Un is the nth partial sum. Okay. Here 3 partial sum, 2 partial sum, single value. First of all, U1 is single value, single term. U1 plus U2 is the here sum of 2 terms. U1 plus U2 plus U3 is the sum of 3 partial terms. Next one U1 plus U2 plus U3 plus n so on. Un is the sum of the nth partial sum. Okay. This is the right hand side. This is the right hand side. RHS. Right hand side. Okay. This is the left hand side. Left hand side is S1, S2, S3, and so on. Sn. Here I'm writing S1, comma, S2, comma, S3, and so on. Sn. It is a sequence. Okay. Here write down Sn is a sequence. Sn is a here sequence. Okay. Here Sn means sum of the Sn. Only Sn is equal to how much? Only Sn is equal to only Sn. Here I'm taking a box. Only Sn is equal to how much? Sum of n partial terms. Sum of n partial terms. Okay. Sum of n partial terms is Sn. Only single Sn is equal to. Okay. This is the inner meaning of the first two lines. First two lines. Okay. I am again reading this definition. First of all, definition given a sequence Un, a real number of real numbers. Un is a sequence of real numbers. Un is a sequence of real numbers. The sequence Sn defined by the sequence Sn defined by only single Sn only single Sn defined by, how it is defined here, Sn is equal to summation k is equal to 1 to n, uk is equal to u1 plus u2 plus sin so on un is called a sequence of partial sums. The sequence of partial sums. Okay, I given explanation before. I given a explanation. S1 is equal to u1, S2 is equal to u1 plus u2, S3 is equal to u1 plus u2 plus u3, and so on. Sn is equal to u1 plus u2 plus sin so on un. Sn is the only single n sequence of n partial sums. Okay, I am taking only Sn, not S1, S2, S3, and so on. Okay, is called a sequence of partial sums of the infinite series. It is denoted by summation n is equal to 1 to infinity un. Ikkada nenu un is the limited, means finite numbers. It is n is equal to 1 to infinity. Infinity terms. Infinity terms means the sum of infinity terms means infinite series. Okay, this is the last one. Sum of infinite terms. And next one, the sequence Sn is converges to small s as the natural number is approaches to infinity. The series is set to converge. Sn is converges. Tends to means converges to small s as n tends to infinity. Okay, na? To the sum s, and is called the convergent series. Convergent series is denoted by, their convergent series is denoted by this one. Summation n is equal to 1 to infinity, un is equal to s. Nth partial sum is equal to how much? S. Nth partial sum is equal to how much? It is s. Infinity partial sums is equal to how much? S also. Infinity partial sums is equal to s also. Here given summation n is equal to 1 to infinity. Un means sum of the infinite terms. Sum of the infinite terms is equal to how much? Is equal to s, small s. Okay, now it is given in the definition. Okay, next one. Example. Suppose one example I am taking. And next one, if the sequence is then divergent, there is no sum. There is no sum exists here. Sum of the infinite terms is equal to, here not giving it, it will give a infinity term. Two answers is giving, it will diverge. Summation n is equal to 1 to infinity un is divergent. Sequence is divergent. Series is also divergent. Sequence is divergent. Series is also divergent. Simply you can ignore. Simply remember. You must remember. 4.2.2 example here. Consider the infinite geometric series. Here summation n is equal to 1 to infinity un is equal to how much here? 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus and so on plus 1 by 2 power n is given here. This is the infinite geometric series. Infinite geometric series. Here to take the nth term, nth partial terms, nth partial sum. Nth partial sum is how much here? Here onwards. Therefore, you can take here un to take a sequence here. Sn is equal to, here first of all un is equal to how much? Only 1 by 2 power n. Un is equal to how much here? 1 by 2 power n. Next one, take a nth partial or infinite partial sums here. Sn is equal to how much? 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 plus and so on 1 by 2 power n. Okay, nth partial terms. This is a geometric progression. This is a geometric progression. This is a geometric progression. Next page I am opening. Next page opening. Some more disturbances. Okay, here this is the geometric progression. The geometric progression principle is how much here? Sn is equal to a into 1 minus r power n by 1 minus r. Here r is less than 1 condition. Why? Because the problem is giving 1 plus 1 by 2 plus 1 by 2 square and plus and so on plus 1 by 2 power n is given. Okay, plus and so on. Okay, here 1 by 2 means less than 1. 1 by 2 square is also 1 by r less than 1. 1 by 2 power n is also r less than 1. Therefore, the geometric series giving a principle r less than 1 condition. R less than 1 condition. The principle is here Sn is equal to a of 1 minus r power n by 1 minus r. Here first term is a. First term is small a is equal to 1. And common ratio r is equal to how much here? 1 by 2. Here first term is 1. No? Next one 1 by 2, 1 by 2 square plus 1 by 2 cube and so on. You can take here. Okay, what is the difference between 1 minus 1? 1 and 1 by 2, it is the difference is common difference is 1 by 2. And next two terms is 1 by 2. Same, next two terms is 1 by 2. The common ratio, common difference is how much here? 1 by 2. This is common ratio or common difference is denoted by small r. Therefore, r is equal to, small r is equal to 1 by 2. Okay, ai value and r value substituting in the above geometric progression principle. Sn is equal to 1 of 1 minus 1 by 2 power in numerator, and it is denominator 1 minus 1 by 2. Okay, and next one 1 minus 1 by 2 in denominator, taking 2 is LCM. 2 1 is 2 minus 1 is equal to how much? It will use 1 by 2. Therefore, in the next step, here numerator value is also same, 1 of 1 minus 1 by 2 power divided by 1 by 2. Here next one 2 is taking numerator. See, a simplification, 2 is taking numerator. Therefore, we will get how much here? Next step 2 into 1 minus 2 by 1 minus 1 by 2 power n. Okay, multiplying with 2, multiplying with the 2. How much it is? 2 minus 2 by 2 power n. Therefore, how much here? 2 minus, we will get next step is 2 by 2 power n. 2 by 2 power n. It will use here 1 by 2 power n into 2 power minus 1. Here, bases are same. Base is 2 here. Powers is n and minus 1. Therefore, I am subtracting here 1 by 2 power n minus 1. Therefore, this is the simplification of Sn. This is the simplification of Sn up to here. Okay, next one. And here applying both sides, the limit n tends to infinity. How much it is? Limit n tends to infinity. I am taking here. Limit n tends to infinity. Sn is equal to limit n tends to infinity 2 minus 1 by 2 power n minus 1. It will use how much here? Here limit 2 is equal to 2 and limit 1 by 2 power n minus 1 is equal to how much it is? Limit 1 by 2 power infinity minus 1. Therefore, it will use 1 by 2 power infinity. Next step 1 by 2 power infinity is equal to how much? Infinity only. Therefore, next step 1 by 2 minus 1 by infinity is equal to how much? 0. Therefore, it will use 2. 2 minus 0 is equal to how much? 2. Okay. Limit n tends to infinity Sn is equal to how much? It is giving the answer is 2. Means it means what here? The geometric progression, the given problem in page number 53. In page number 53, the problem, sum of the n terms is giving 2. Okay. The sequence Sn converges. The sequence Sn converges to 2. By definition, summation Gn converges to 2. So that summation n is equal 1 to infinity 1 by 2 power n is equal to how much it is giving? 2. It is also giving 2. This is our first example. Next one, page number, next page I am opening. A simple problem in the geometric series. And next one, it is completed. Next 4.2.3 example, page number 54. Consider the series summation n is equal 1 to infinity 1 by n into n plus 1. Here let it take here un is equal to 1 by n into n plus 1. Okay. Here a simplification is giving here 1 by n minus 1 by n plus 1. First of all, to take this one 1 by n minus 1 by n plus 1. Okay, here LCM is how much? N into n plus 1. How much it is? N cancel, we will get how much? N plus 1. Okay, in the numerator. And next one, n plus 1 cancel, how much it is? Minus n. Minus n plus n cancel, we will get how much here? LCM is n into n plus 1. We will get how much? Only 1. Okay, this is our problem. Okay, this is our problem. It is giving. Okay, after the simplification, 1 by n minus 1 by n plus 1 is giving how much? 1 by n into n plus 1. 1 by n into n plus 1. Therefore, we can write. Therefore, we can write 1 by n into n plus 1 as 1 by n minus 1 by n plus 1. Here, you can apply n is equal to 1. How much it is? 1 by 1 minus 1 by 1 plus 1 is equal to how much? 1 minus 1 by 2. Next one, n is equal to, you can apply here. U2 is equal 1 by 2 minus 1 by 2 plus 1 is equal to how much? 1 by 2 minus 1 by 3. And next one, Sn. Sn is equal how much? You can write down and so on. You can write down. Sn is equal summation k is equal 1 to n. Uk is equal how much? 1 minus 1 by 2 is one bracket plus 1 by 2 minus 1 by 3 is another bracket. Plus and so on. 1 by n minus 1 by n plus 1 is another bracket. Okay. Here a simplification 1 minus 1 by 2 plus 1 by 2 cancel, minus 1 by 3 plus 1 by 3 next term is cancelled. 1 plus 1 by n and minus 1 by n is cancelled. We will get how much? At least at last we will get how much it is. Sn is equal to how much? 1 minus 1 by n plus 1. Only these two terms will be there after the cancellation. Okay. And therefore, Sn is equal to how much? Summation k is equal to 1 to n. Uk is equal to how much? 1 minus 1 by n plus 1. Here, both sides you can apply limit. Limit Sn is equal to how much? Limit of 1 minus 1 by n plus 1. Okay. Limit of 1 is equal to how much? Only 1. Limit of 1 by n plus 1 is equal to how much? 1 by infinity. 1 by infinity is equal to how much? Here 1 minus 0. Therefore, we will get how much it is? 1. Here limit of 1 by n plus 1 is equal to 1 by infinity plus 1. 1 by infinity plus 1 is equal to how much? 1 by infinity. 1 by infinity is equal to how much? 0. Okay. Here, this is the simplification of limit to 1 by n plus 1. It will give 0. Therefore, 1 minus 0 is equal to how much? It is 1. Limit of Sn is equal to how much? The given series converges to 1. The given series is converges to 1. This is the 4.2.3 example in page number 54. And next one, the next problem. And next one, this is very important problem. 4.2.6, it is a previous problem. The series summation n is equal to 1 to infinity 1 by n is not convergent. Here the previous two problems is convergent. Here 4.2.2 problem and 4.2.3 problem. In page number 53 and page number 54 gives convergent. But here 4.2.6 problem, it is not convergent. How it is possible? We can see here the sequence 1 by n converges to 0. Here it is a sequence, it is a series. Series is given, series is not convergent, but the sequence is converges. Series is not convergent, but sequence is convergent. Sequence is convergent to 0. How it is possible? Limit n tends to infinity. 1 by n is equal to how much? 1 by infinity. It will give how much? 0. 1 by n is converges to 0 in sequence. But it is not a sequence. It is a series, not convergent. Okay. The series summation 1 by n diverges. Series is diverges. Okay. How it is possible? Okay. We can see in several steps here. A subsequence of the sequence to take here subsequences of sequence 1 by n. It is not bounded. Subsequence is not bounded. Therefore, the sequence is not bounded. Subsequence is not bounded means the sequence is also not bounded. How it is possible? To take here SN1, SK1, here SNR or SKR are subsequences. SN is sequence. SNR comma SKR is subsequences. Okay. Here to take here SK1 is equal 1 by 1 plus 1 by 2. SK2 is equal how much? To take 4 terms here. 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. But here to compare this one, 1 by 1 plus 1 by 2 is equal how much? SK plus 1. Here SK plus 1. Okay. And the remaining terms 1 by 3 plus 1 by 4 is as it is. Okay. Here I'm changing and I'm comparing SK2 with here 1 by 3. Here replace to 1 by 4. 1 by 3 replace to how much here? 1 by 4. Therefore, the equal changes to greater than. The equal changes to greater than. SK2 greater than. Here SK2 greater than SK1 plus 1 by 4 plus 1 by 4. 1 by 4 plus 1 by 4. Already it is a greater than value. Already it is a greater than value. Therefore, you can write down 1 plus here. Actually, SK1 is equal how much? SK1 is equal how much? It is SK1 is equal 1 by 1 plus 1 by 2. Write down here. 1 by 1 plus 1 by 2 is equal 1 plus 1 by 2. And the next step is 1 by 4 plus 1 by 4 value is how much here? Here simplification 1 by 4 plus 1 by 4 is equal how much? 4 is the LCM 1 plus 1. It is 2 by 4. 2 by 4 means how much? It is 1 by 2. Okay, it will give 1 by 2. Okay, here is SK plus 1 plus 1 by 2. SK plus 1. SK plus 1 means 1 plus 1 by 2. And the remaining 1 by 4 plus 1 by 4 value is 1 by 2. Therefore, the total SK2 is how much? SK2 is greater than how much it is? SK2 is greater than 1 plus 1 by 2 plus 1 by 2 is equal to how much? A simplification we will get how much? 1 by 2 plus 1 by 2 means how much it is? To take here LCM is 2, 1 plus 1 is equal to how much here? 2 by 2 is giving. Okay, therefore it will give here how much it is? Total answer is SK2 greater than 1 plus 2 by 2. Similarly, SK3 is also how much? 1 plus 3 by 2. And so on. SKR is greater than 1 plus R by 2. SKR is greater than 1 plus R by 2. Okay, you can apply here limit. You can apply here limit. How much it is? It will get here limit R tends to infinity 1 plus R by 2. How much it is? 1 plus infinity by 2. 1 plus infinity by 2 means how much? It is 1 plus infinity. 1 plus infinity is equal to how much? Infinity. Okay. Infinity means it is divergence. It will not be getting any values here 0 or 1 or 2 or anything. It is giving only infinity. Therefore, the subsequence is divergence. The subsequence is divergence. You see, divergence means it is not convergent. It is not convergent. I am underlining. The subsequence SKR is not bounded and it is not convergent. Hence, it is not convergent. Therefore, the sequence Sn is equal to 1 by n is also not bounded and not convergent. The subsequence is not bounded and not convergent. Therefore, the sequence is not convergent. Therefore, hence, the series, infinite series, summation n is equal to 1 to infinity 1 by n is not convergent. Next one. Next page. Next one, theorems on series of positors, page number 55. It is 4.3.1 theorem. Okay, it is very easy theorem. Let the summation n is equal 1 to infinity a n and summation n is equal 1 to infinity b n be two infinite series. How many infinite series is given here? Two infinite series. First infinite series is summation n is equal 1 to infinity a n. And second infinite series is summation n is equal 1 to infinity b n. This is two infinite series. Converges to how it is possible here. First infinite series is converges to L. A n is converges to L. And b n is converges to m. Then for numbers here given p and q, the series is written as summation n is equal 1 to infinity p a n plus q b n converges to pl plus qm. Pl plus ql. This is the our given positive terms of the series theorem. Okay, some of the two series it is converges and converges to pl plus qm. The proof. First of all, you can take the sequences. How many sequences here? Three sequences. Capital A n is a sequence, comma capital B n is a sequence, and capital C n is a three sequences. Here denote the partial sums of the sequences. Here sequence A n is partial sum means how much it is? Summation n is equal 1 to infinity A n and summation B n is The partial sum is summation n is equal 1 to infinity bn, and summation sequence cn is equal to how much? Summation n is equal 1 to infinity pan plus a qbn. Then here cn is equal to how much? K is equal to 1 to n pak plus qbk is equal to how much? P into summation k is equal to 1 to n ak plus q into summation k is equal to 1 to n bk. Okay, here how much it is? Here the value is how much? Here pan plus a qbn. Here an is converted to l and bn is converted to m. As n is the natural number, infinity natural number, we will get how much? Here cn is converted to pl plus qm as n tends to infinity. Here the sum of the sum of the nth terms, summation n is equal 1 to n, ak is written as a sequence an. Summation k is equal 1 to n, bk is written as a sequence of bn. Here the total answer is pan plus a qbn. Here the sequence an is converted to small n, and the sequence bn is converted to small n, where n is a natural number, n is approaches to infinity. Therefore, Cn, the sequence Cn is converted to PL plus Qm as n tends to infinity. This is our 4.3.1 theorem. Next one. Next 4.3.2 theorem here. Next one. If the series summation n is equal 1 to infinity an is convergent, then an is converges to 0 as an is converges to 0. An is converges to 0 as n tends to infinity. This is also important theorem. Here the series summation n is equal 1 to infinity an is convergent. The infinite series, how much it is? It is convergent here. It is convergent. Summation n is equal 1 to infinity means the sum of the infinite series, sum of the infinite partial sums, sum of the infinite partial sums. An is convergent. Then an is converges to where? Here 0. An is equal to how much? It is giving a 0 as n tends to infinity. The natural number is approaching infinity. The sequence an is converges to 0. How it is? The answer we will get here. Okay, here let us to take the proof. Here let us sequence Sn be the partial sum sequences. Sn is the partial sum sequences of the given series. Here Sn is equal to, by taking here a1 plus a2 plus a3 plus and so on an. Sn is equal to what here? Nth partial sums. Here n belongs to z plus here. Okay, only positive partial sums. And Sn minus 1 is equal to how much here? a1 plus a2 plus a3 plus and so on an minus 1. Here n belongs to z plus positive numbers. Means here n minus 1, n minus 1, n minus 1 partial sums. N minus 1 partial sums. We are taking here subtraction. Sn minus Sn minus 1. A1 cancel, A2 cancel, A3 cancel, an minus 1 cancel. Only on the right hand side we will get only an, and the left hand side we will get Sn and Sn minus 1. Left hand side is Sn minus Sn minus 1, and the right hand side is only we will get an. Okay, here we will get how much here? An is equal to Sn minus 1 for all n. Okay, yet we know the sequence Sn is converted to L, and sequence Sn minus 1 is also converted to L. Therefore, we can apply here both sides by limit n tends to infinity. Limit n tends to infinity an is equal limit n tends to infinity Sn minus 1. Here, multiplying with limit n tends to infinity, we will get next step is limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1. Therefore, Sn is converges to L, and Sn minus 1 is also converges to L. Therefore, L minus L is equal to how much? 0. Therefore, here an is converges to how much here? 0, where n is approaches to infinity. N is natural number is approaches to 0. Here an approaches to 0. This is the theorem. This is the theorem. Next one, we can. Okay, we have saw this theorem. Here we can take a example 4.3.6. 4.3.6 by using this theorem, how we will get the answer. Okay, here 4.3.6 page number 57. The series summation n is equal 1 to infinity. N by n plus 1 is divergent. The series summation n is equal 1 to infinity. N by n plus 1 is divergent. How it is possible to divergent? We will get a solution here. An is equal to take n is equal how much here? N by n plus 1. Here in the numerator n is as it is, denominator n is common. We will get how much? N of 1 plus 1 by n. Here numerator n and denominator n is cancelled. And next step we will get how much? N is equal 1 by 1 plus 1 by n. Approach here both sides we can apply limit n tends to infinity. Limit the next step will be we will get here limit n tends to infinity. An is equal limit n tends to infinity 1 by 1 plus 1 by n. Here you can apply here in the place of n infinity. Next step 1 by 1 plus 1 by infinity. Okay, 1 by infinity is equal how much? 0. We know this one. 1 by 1 plus 0. Okay, 1 by 1 plus 0 is equal how much? 1. Here it is not giving 0. It is giving 1. Therefore, it is not is equal to 0. Therefore, limit n tends to infinity n is equal how much? It is 1. Therefore, limit n tends to infinity n is equal how much? It is 1, not is equal to 0. An is not converges to 0 as n tends to infinity. Therefore, summation an is not convergent. Summation an is not convergent. Why? Because in the previous theorem 4.3.2, the series summation n is equal to 1 to infinity an is equal to 0. But here the answer is 1. Therefore, it is contradiction. Therefore, it is not convergent. Okay. And next one. Next one. Four point three point eight theorem. 4.3.8 theorem. This is the Cauchy's general. This is the page number 57. Cauchy's general principle of convergence. Cauchy's general principle of convergence. A series summation is equal 1 to infinity an is convergent. If and only if to each delta greater than 0. Delta greater than 0 is here positive real number. There exists a natural number capital N such that for each a comparison between natural numbers small m greater than or is equal to capital N. The here natural numbers are m is greater than value. Next number is small n, and next number is capital N. Yeah, it is a small differences in natural numbers here. Okay. Here the series, some of the series is mod is given here, mod of an plus 1 plus an plus 2 plus n so on plus am. It will give, you see, it is the value is less than delta. It gives the value is less than delta. I am again reading this one, the statement of the Cauchy's general principle of convergence. A series summation here infinite series n is equal 1 to infinity an is convergent. Infinite series is convergent here given. If and only if to each delta greater than 0, there exists capital N such that for each number m, small m is greater than small n. Greater than is equal to capital N. Mod an plus 1 plus an plus 2 plus n so on am is less than delta. Proof here. Let we can take here, we can assume here two series. First series is Sm and second series is Sn. Yeah, here first series is m partial sums and second series is n partial sums. Okay. Here to take m terms and n terms. Here Sm is equal to I am exploring here a1 plus a2 plus a3 plus and so on an plus 1 plus an plus 2 plus and so on am. This is the m term of Sm. And next one you can write down Sn is equal to a1 plus a2 plus a3 plus and so on an. How many terms here? N terms. Okay. You can here next step is subtracting Sm minus Sn. Next step is what here? Sm minus Sn. A1 cancel, A2 cancel, A3 cancel, An cancel. Remaining is left hand side is how much here? Sm minus Sn is equal to right hand side is how much? How many terms we are? An plus 1 plus An plus 2 plus and so on Am. Okay. Here next one Sm minus Sn is how much it is? Sm minus Sn is equal to an plus 1, an plus 2 plus n so on am. Okay. Therefore, Sm and Smr is in infinite series. Summation n is equal 1 to infinity. Summation n is equal 1 to infinity an. But here in the statement n is equal 1 to infinity an is what here it is convergent. If and only if a sequence Sn is also convergent. If and only if a sequence Sn is also converges. Means Sm minus Sn is also converges. It means by the Cauchy principle, Sm minus Sn is also converges. Converges. How much the converges is less than delta. Here delta value is how much it is greater than 0. Where it is convergent, small m greater than n greater than or is equal to capital N. Thus, the general principle, last one, the general principle of efficiency, the theorem is true. The theorem is true. Okay. The value is how much it gives less than delta. Okay. This is the Cauchy general of convergence. 4.3. Okay. Next one. Next page I'm opening. Here it is not opening. What happened? Okay, next one 4.3.9 number system. Princeton. Princeton we can prove by using our the sequence, given sequence n is decreasing sequence of positive terms, decreasing sequence of positive terms, and the series summation n is equal 1 to infinity an is convergent. Okay, here Princeton scientist is given what here decreasing sequence and the positive terms, decreasing sequence of positive terms. It is convergent. It is convergent. Here the convergent is explaining here n into an is converges to 0. Here in the previous problem 4.3.6 it is in this one it will give 1. 4.3.6 example problem. It gives only 1. Answer is converges to 1. But the theorem 4.3.2 gives only 0. An is converges to 0. It is convergent. An is converges to 1. It is not convergent. Okay. Here also Princeton scientists it is decreasing sequence of oscillons and it is converges to 0 as n tends to infinity. This is the Princeton statement. We can prove here delta greater than 0. It is a positive real number by Cauchy principle. We have studied just before Cauchy's general principle of convergence 4.3.8. There exists a capital N here Sm m terms minus n terms. It will give how much is am plus 1, am plus 2 plus n so on an. Okay, you can write down here summation. Summation k is in the shortcut form. Summation k is equal to m plus 1 to n ak. The value is giving here delta by 2. Here actually delta is greater than 0, but here the value is how much here? It is less than delta by 2. Delta is greater than 0 and delta by 2 is a small value. Okay, need not worry to taking this delta by 2. Okay, for all here the natural numbers are n greater than small n greater than small n is greater than or is equal to capital N. Okay, we are taking here the value is n greater than 2n plus 2 capital N plus 1 implies here 1 is taking left hand side. How much it is? N minus 1 greater than 2n. And next one 2 is cross multiplying. How much it is? N minus 1 by 2 greater than n. Okay, n minus 1 by 2 greater than capital N. And here we are taking here how much it is? N minus 1 by 2. N minus 1 by 2. The natural number is n minus 1 by 2 and greater than n. Okay, the infinite series summation ak is giving less than delta by 2, where summation is over k and the natural number is n minus 1 by 2 less than k less than or equal to small n. Okay, this is the actual natural numbers between n minus 1 by 2 to n. Okay, but it is a decreasing sequence. It is a decreasing sequence. The decreasing sequence is a notation. Here we are taking ak is greater than or equal to an, and the number of terms is less than or equal to n plus 1 by 2. Here how many terms here? N plus 1 by 2 less than or equal, less than or equal to n plus 1 by 2. Number of terms are in the decreasing sequence. The decreasing sequence notation here ak is greater than or equal to an. Here taking summation here infinite series summation. Here n is equal 1 to infinity ak is greater than n by 2 an. Thus n into an is less than delta by using Cauchy's general principle. Here nan is less than delta for all n greater than 2n plus 1, or nan tends to 0 as n tends to infinity. This is the Princeton principle. Okay, next one. Princeton principle. Next one, we're taking one absolute convergency definition. Absolute definition here 4.3.11 page number 58. This is the absolute convergency definition. An infinite series, we are taking infinite series summation n is equal to 1 to infinity an is said to be absolutely convergent or converges. Absolutely convergent or converges absolutely. Okay, both are same words here. Absolutely convergent or converges absolutely same. If the series summation n is equal to 1 to infinity mod an. Actually, it is a infinite series. Then here it is given absolutely convergent infinite series. Absolutely convergent infinite series is converges. Okay, this is the definition. This is the definition. It is ordinary infinite series. This is a absolutely infinite series. Absolutely infinite series. Absolutely infinite series is what here? Convergent. This is the definition. And next one, a series is not absolutely convergent. It is called conditionally convergent series. Conditionally convergent series. Okay. And next one here, 4.3.12 theorem here. Every absolutely convergent series is convergent. Absolutely convergent series is convergent. Not here convergent to absolutely convergent. Only absolutely convergent series is convergent. Okay. It is given. Okay. So here the proof here. Suppose n is equal 1 to infinity mod an is convergent. Suppose we are taking here how much here? Summation n is equal 1 to infinity mod an is convergent. Let to take here delta greater than 0, it is a positive real number. By Cauchy's general principle, we get here convergency. Sm minus Sn is equal how much here? Mod am plus 1 plus am plus 2 plus and so on an. Okay, here by taking each term as mod. Therefore, we will get how much here? Mod am plus 1 plus mod am plus 2 plus and so on. Mod an is less than delta for all n greater than small n greater than small n greater than is equal to capital N. Okay, here a inequality we will get here how much here? Mod am plus 1 plus am plus 2 plus and so on an is less than or is equal to mod am plus 1 plus mod am plus 2 plus and so on mod an. Okay, it is by using the triangle inequality we will get how much it is by Cauchy system. It will give less than delta. Okay, here summation n is equal 1 to infinity an convergence by Cauchy principle. Therefore, it is the absolutely convergent series is convergent. Okay, next one. I'm opening next one. Here 4.3.13 page number 59. Okay, example the series summation n is equal 1 to infinity minus 1 whole power n minus 1 by n is equal to how many terms it is giving here? Plus 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus and so on. is convergent. Here in this example, it is given a infinite series like this. So summation n is equal to 1 to infinity minus 1 whole power n minus 1 divided by n. Okay, it will gives what here? Suppose n is equal to 1, gives plus 1, n is equal to gives minus 1 by 2, n is equal to 3 plus 1 by 3, n is equal to 4 minus 1 by 4 plus and so on. It is convergent series. Okay, and it is not absolutely convergent. It is not absolutely convergent. Why? Because it is some are negative terms is there, and it is not and taking a subsequence, we will not getting, it is not absolutely convergent, or any reason is behind in this problem, we can check. Okay, we can check in the solution. Okay, first of all, let us consider here, let n is equal here, let summation k is equal to n plus 1 to infinity. K is equal to how much? N plus 1 to infinity, not n is equal to 1 to infinity. We are taking here n plus 1 to infinity by using Cauchy's general principle. We are using Cauchy's general principle of this example. Okay, here you can apply here in the place of k, you can write down n is equal to k is equal to n plus 1. Therefore, how much? First term is 1 by n plus 1, and the next term is how much? Minus 1 by n plus 2, and n is equal k is equal to n plus 3. We will get how much? Plus 1 by n plus 3, and minus 1 by n minus n plus 4, and plus and so on, minus 1 whole power n minus 1 by m. Okay, this is the uh, m minus n minus 1 terms. Okay, here next one is here first two terms, to take first two terms. Okay, a calculation of first two terms. Here the first two terms LCM is how much? N plus 1, n plus 2. Okay, here after LCM in the numerator is n plus 2 minus minus n minus 1. Okay, here n cancel. Next one, 2 minus 1 is equal to how much? We will get the answer. First term is 1 by n plus 1 into n plus 2. And next, to take the second and third term, the LCM is n plus 3, n plus 4. Okay, here in the numerator n plus 4 minus n minus 3, n cancel here also, and 4 minus 3 is equal to 1. Therefore, how much it is giving? 1 by n plus 3 into n plus 4. Okay, here a small change. It is a equal. This is equal. Okay, this is equal. Here also equal. Here also equal. But it is less than. Okay, a small change is required here in this second term too, and so on. A small change, n plus 3 to n plus 2. Therefore, the value is here. Some of the comparing to left hand side, some of the value is increasing here. Okay, therefore it is less than. Okay, first term is how much? 1 by n plus 1 into n plus 2, and the next one is 1 by n plus 2 into n plus 3. Okay, next after you can rearrange this one. First term as 1 by 1 plus 1 by n plus 1 minus 1 by n plus 2. Next term you can rearrange this one, 1 by n plus 2 minus 1 by n plus 3. After LCM, we will get the same above step we will get. The same above step we will get here. Okay, now. Next one here, a simplification is needed here. Minus 1 by n plus 2 and plus 1 by n plus 2 is cancelled. And next one, minus 1 by n plus 3 and plus 1 by n plus 3 and plus and so on, so forth. We will get at last here only two terms. Okay, here only two terms we will get here. One is even term, one is odd term. You can take any one. Okay, 1 by n plus 1 minus 1 by n plus p plus 1. After cancelling this term, so we will get only two terms. First term is, it is a even term, 1 by n plus 1 minus 1 by n plus p plus 1. Suppose it is odd term, 1 by n plus 1 minus 1 by n plus p plus 1 plus 1 by m. This is odd term, this is the even term. Okay, R is required here. Okay, here I am taking only even term. Here to take it is less than 1 by n plus p plus 1. Here it is a even term, to take 1 by n plus 1 plus 1 by n plus 1. LCM is n plus 1 in the numerator 1 plus 1. Here we will get how much? 2 by n plus 1. Here it is less than 2 by n plus 1, and you can write down this one 2 by n plus 1 is equal to 2 by n. It will not change any value. Why? Because it is less than. It is less than. Here a Cauchy natural number here m greater than n greater than 2 by delta. Okay. Here the 2 by n value is how much here? 2 by n value limit here limit 2 by n value is how much here? 2 by n is equal to 2 by infinity. 2 by infinity is giving 0. Therefore, the given series is converges. Okay, by using Cauchy principle, the given series is converges. Okay, therefore it is not absolutely convergent. Only the problem is going on only converges, not here taking any absolute value. Okay, therefore summation mod an is equal to summation 1 by n is not convergent. It is not required here. Next one. Next, it is unit 4 is completed. Next one, unit 5. Okay, unit 5. I am opening unit 5. So many tests are we required to find the solution of the infinite series. Okay, here unit 5 test of convergency. Here test of convergency means it is a comparison test is there, a p-test is there, comparison test is there, ratio test, Cauchy's root test, D'Alembert's ratio test, and Cauchy's condensational test. So many tests are there here. We have total 6 tests are in this unit 5. I will explain one by one. First of all, to taking here test of convergency. Okay, here test of here. Suppose a series problem is given. Suppose a series problem is given. Uh, we uh, we may compare. We may some confusion is uh, experienced in the given problem. Why? Because what type of test we can use? What type of test we can use? How to solve this problem is a confusion is in our mind. Okay, the test will use the test. These 6 tests gives. It will not confuse after explanation of these 6 tests and giving some examples. The doubt is clear and it will easy to solve the problem of some of the series. Okay. Here, first of all, 5.1 test of convergency. Here, if summation un is the given series and if summation vn is the selected series. Okay. Un is given series. Okay. Here, our assumption is summation vn is the selected series. Okay. It is convergent. Then summation un is convergent. If we are requiring it is a comparison. Un is less than or equal to Vn. Why? Because Vn is selected terms, selected series of terms for each n. Similarly, summation Vn is divergent. Then summation Un is also divergent. Okay, now. First of all, here in this explaining here, summation Un is convergent. Summation Un is convergent. And Un is less than or equal to Vn is required for each n. Okay, it is convergent. And similarly, suppose summation Vn taking summation, it is first step. This is the second step. In the first step, summation Un is convergent. Then a comparison. Next Vn is convergent. Here in the second step, summation Vn is divergent. The inequality Un is greater than or is equal to Vn. Inequality is here Un is greater than or is equal to Vn. Comparison is it is decreasing, and similarly Vn summation Vn is also divergent. It is in the first step. It is an increasing sequence. It is an increasing sequence, and the summation Vn is convergent. Therefore, summation Vn is convergent in the test of convergency. Okay, it will be must be checked. A given series is first of all in our mind to check this one. Un is less than or is equal to Vn, or Un is greater than or is equal to Vn. And suppose to take here Vn is the selected terms. So these 3 steps we must require to solve the infinite series. Okay. Next one, 5.1.1. The page number is here, page number 62. Theorem t-test. T-test. Okay. I will complete in this 5 minutes. Okay. An infinite series of positive terms. Infinite series of positive terms. No negative terms is required here. Only positive terms. Okay. Here the infinite series is how much it is? Summation n is equal to 1 to infinity 1 by n power p. It is convergent. Okay. The infinite series is convergent. When p greater than 1. It is condition is given. P greater than 1. It is convergent. Otherwise, means it is p less than or is equal to 1. It is divergent. Here two conditions are raised in the theorem 5.1.1. P greater than 1. You must remember this one. P greater than 1. It is convergent. P is less than or is equal to 1. It is divergent. Okay. This is the theorem. Okay. Next to proof. First proof. P greater than 1 to take first condition, and second condition is p less than or equal to 1. Okay, proof. First of all, let Sn be the partial sum of the first n terms. You can take here partial sum. To take a partial sum of the first n terms. Next we will calculate. Okay, next page. Next page. Here, case 1, let p greater than 1. Here, to take first term is 1 by 1 power p is equal to how much? 1 by 1 power p. 1 by 1 power p. Means here how much? 1 by 1 power p is equal to how much? 1. 1 power is equal to 1. 1 square is equal to 1. 1 cube is equal to 1. 1 power n is equal to 1. Also 1 power p is equal also 1. Therefore, 1 by 1 is equal to how much? 1. First term completed, you can take two terms. 1 by 2 power p plus 1 by 3 power p. Okay, you can replacing after n. I am substituting n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7, and so forth. Okay, here n is equal to 2 and n is equal to 3 in the next two terms. 1 by 2 power p plus 1 by 3 power p. I am comparing here less than the value 1 by 2 power p plus 1 by 2 power p. Here 1 by 2 is equal to how much? 0.5. And 1 by 3 is equal to how much? 0.33. Okay, next one, 1 by 4 is equal to how much? 0.25. And 1 by 5 is equal to how much? 0.2. It is a decreasing here. 1 by 2 value is greater than comparing to 1 by 3. And 1 by 3 is greater than 1 by 4. And comparing 1 by 4 is greater than 1 by 5. Okay. It means 1 by 2 is greater than that. Therefore, here also same comparison. 1 by 2 power p plus 1 by 3 power p is less than how much it is? 1 by 2 power p plus 1 by 2 power p. Okay, LCM is how much here? It is 1 by 2 power p is LCM. Okay, 2 power p is LCM. In the numerator 1 plus 1. Okay, how much it is? 2 by 2 power p. 2 by 2 power p. 1 by 2 power p into taking 2 power minus 1 here in the denominator. Okay, bases are same, powers are here subtracted. Therefore, we will get how much? 1 by 2 power p minus 1. Okay, it is less than 1 by 2 power p minus 1 is here. Okay, two terms 1 by 2 power p plus 1 by 3 power p is how much? Less than 1 by 2 power p minus 1. Next year, first term completed and the second two terms completed. Next year, I'm taking four terms here. 1 by 4 power p plus 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p. The value is comparing with the 1 by 4. Okay, comparing here 1 by 4 is equal to how much? 0.25. 1 by 5 is equal to 0.2. And 1 by 6 is equal to how much? 0.16. And 1 by 7 is equal to how much? 0.4. 0.14. How much it is? 0.14. Okay, the value is decreasing. 1 by 4 value is greater than comparing with 1 by 5. 1 by 5 value is greater than comparing with the 1 by 6. 1 by 6 value is greater than comparing with the 1 by 7. Therefore, you can take here 1 by 4 is greater than value. Therefore, I can write here 1 by 4 power p plus 1 by 4 power p plus 1 by 4 power p. Okay. How much it is? 1 by 4 power p plus 1 by 4 power p plus 1 by 4 power p plus 1 by 4 power p. 4 power p is LCM 1 plus 1 plus 1 plus 1. Okay, how much it is? 4 by 4 power p. Here 4 is taken denominator. It will give 4 power minus 1. Okay, bases are same, powers are subtracted. Therefore, we will get 1 by 4 power p minus 1. Okay, here how much it is? It is how much here? 4 means how much it is? Only it is 1, not 2. It is 1. A small mistake. 1 by 4 means 2 square. 4 means 4 is equal how much? 2 square. 4 means 2 square. Therefore, 2 square into p minus 1. Okay. The four values is how much it is? Less than 1 by 2 square p minus 1. Same similarly, here how many terms are completed here? First of all, only single term we can take here. How many terms? 2 terms. Here 4 terms. The next term is 8 terms we are taking. 1 by 8 power p plus 1 by 9 power p plus and so on 1 by 15 power p. Okay. Comparing with 1 by 8 power p plus 1 by 8 power p plus and so on 1 by 8 power p. Here adding here LCM is 8 power p. Adding all these once we will get how much? 8 by 8 power p. How much it is? 1 by 8 power p minus 1. We will get 8 means 1 by 2 cube into p minus 1. Okay. Next page. Okay. I will close in 2 minutes. 2 more minutes. Okay, here and so on, adding all these terms, the left hand side is the sum of 2n terms. How many terms I've taken? First of all, 1 term, తర్వాత 2 terms, next one 4 terms, తర్వాత 8 terms, తర్వాత 16 terms. We will get and so on so forth. We will get how much? 2 power n terms in the left hand side. Okay. In the right hand side, what will happen here? 1. 2 terms gives 1 by 2 power p minus 1. And 4 terms gives 1 by 2 square into p minus 1. Okay, 8 terms is given 1 by 2 cube into p minus 1. Okay, adding all these on the right hand side. Only left hand side is only 2n terms. Left hand side is only 2n terms. Okay, it is a sequence. Okay, here S2n is less than right hand side is adding all these terms 1 plus 1 by 2 power p minus 1 plus 1 by 2 square into p minus 1 plus 1 by 2 cube into p minus 1 and so on. The right hand side is a geometric progression. It is a geometric progression. I explained a starting problem of geometric progression. You will get geometric progression. It will give how much it is. It is less than 1. 1 by 2 power p minus 1 is less than 1 because p is greater than 1. P is greater than 1. The sum of the given series is less than or equal to the sum of the convergent series. Therefore, the given series is convergent if p greater than 1. P greater than 1. And next one more condition is there. P is less than or is equal to 1. P is less than or is equal to 1. Here P is less than or is equal to 1. This is the second condition. Oh, sorry. This is the second condition. P is less than or is equal to 1. It is p is less than or equal to 1. Here we can take here 1 by n power p greater than or equal to 1 by n. First of all, to take 2 terms here. At a time 2 terms here. How much it is? To take 1 term, it will give only 1 by 1 power p is equal how much? Only 1. Okay. Next 2 terms 1 by 1 power p plus 1 by 2 power p is greater than or equal how much? 1 plus 1 by 2. Okay. Next one. Next again 2 terms 1 by 3 power p plus 1 by 4 power p. How much it is? 1 by 3 plus 1 by 4. And comparing with the highest term 1 by 4 plus 1 by 4. And LCM is giving 4 and 1 plus 1 is equal to 2. Therefore 2 by 4 it will give greater than 1 by 2. Next 4 terms. Taking 4 terms here 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p plus 1 by 8 power p greater than or is equal to how much? 1 by 5 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Okay, it is greater than or equal 4 by 8 is equal to how much we will get here? 1 by 2. The left hand side is the sum of the 2 power m terms of the given series and S2m is equal to greater than 1 by 2 plus 1 by 2 plus and so on n terms. Okay, it will give what here? 1 by 2 plus 1 by 2 plus 1 by 2. It is the sum of the m terms of the sum of the n terms. Sum of the Nth unsigned, it is last one. Oh, sure. Sum of the, it is what here, sum of the greater than, sum of the series greater than or, here sum of the greater than or equal to an unbounded series. Here 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2 and so on. M terms is given, it is an unbounded series. The sum diverges to here infinity. The given series is divergent. The given series is divergent when the condition is P is greater than or is equal to 1. The condition is P is less than 1. It is giving a convergent. Okay. This is the P series test. Tomorrow, next I will take the comparison test 1 and comparison test 2. And all of you, thank you for listening to this class. Okay. I can stop this lesson.